Okay, so then, of course, my first question would be, what are the three main components of machine learning? Yes, very good. I've seen some answers here. Data model loss. So we want to fit a model to data points. That means we have data points, each characterized by a feature and a label. And we want to find out of a set or a space of different hypothesis maps, which I call model. So a model is a space or a set of hypothesis maps, and we want to find the best one. To find the best one, we need to measure the quality, and we could use, for example, the squared error loss to measure the quality. And so we get one squared error term for each data point. So this would be the third data point. So we get the label of the third data point minus the predicted label value of the third data point square, and we add up all these loss terms to the average loss. So what we get then is, if we assume that the hypothesis is parameterized by weight vector, by weights. For example, if we use a linear model, then each hypothesis map is defined like this, a weighted linear combination. So what we would like to do then is to find the weights that have the smallest loss or average loss on the training error. So we have here this loss or training error, and we would like to find the best weight. So there would be some optimal weights that we would like to find. Yeah, but what is important to remember in machine learning, it's actually not this training error that we want to minimize. What is the ultimate criterion that we want to minimize? What is the ultimate performance measure for a hypothesis? The risk or the expected loss, yes. And this might be different. So here is the risk, depending on the weights or on the model parameters, and this might be defined, for example, using the squared error loss, y minus w transposed x squared. So this here is the predicted label or the prediction, and we would like to minimize this expectation, but we cannot minimize this expectation because in practice we do not know the probability distribution of features and labels. So what we do instead is we minimize the empirical risk, which we can compute. The empirical risk we get by summing the loss over all data points in the training set. So if we have 3 data points in the training set, or let's say m, then we add these losses or squared losses over all data points in the training set. And we hope that this here is a good approximation for the risk, but this might not always be the case. In particular, when is this approximation not good? How do we call such a situation or condition? The bad guy in machine learning is overfitting. Yeah, when we overfit the training set, then this breaks down this approximation. This completely different then, or at least the optimizers, the optima are different between the empirical risk or training error and the risk, the actual risk as expected loss. Okay, so this is important to keep in mind because this tells us, or this suggests, that we should not worry too much about perfectly optimizing the training error. So we should not try to find exact optimum, or we should not invest too many too much computation to find the optimum with a tolerance of 10 to the power minus 20. So with extremely high precision, finding the optimum, because the optimum here is an approximation of the actual optimum, the best hypothesis, which minimizes the risk. And if this approximation here, so let's say this is on the order of 10, then it doesn't make sense if we optimize here to an order of 10 to the minus 10. So high precision optimizers of the empirical risk. It doesn't make sense because the optimum itself is up to an error of 10 away from the actual optimal hypothesis. So it would not help too much if we invest here immense amounts of computation to find the precise optimum of the empirical risk. So today I want to talk about an important family of optimization algorithms that are actually exactly what we want in machine learning. We want a machine learning, we want an optimization algorithm that quickly gets close to a good enough approximation of the optimum. So we start, this is an iterative algorithm. So we start with a first guess for the model parameters. And this I denote W superscript 0. And then what we do is we iteratively, we take turns, so to say, we update the current guess to get a better one, W1, and then an even better choice for the model parameters, W2, and so on and so forth. We do this K times, capital K times. And we hope that this, after K times, we stop, and we hope that this is a good approximation for the solution of the empirical risk minimization. And again, actually, this is not what we're ultimately interested. What we're ultimately interested is the minimizer of the risk. However, we hope that we do not overfit, and the optimizer of this empirical risk is also close to the optimizer of the risk. Okay, and the idea of gradient descent is quite simple. So we look at the function that is assumed differentiable. So at each point, we can compute a local linear approximation. There's a tangent hyperplane in higher dimensions, which is defined by the gradient. So we evaluate the function. This is the function. I call it function, generic function. This could be, for example, the empirical risk. Could be a function. Another function would be the risk. But this function, we do not know. We don't have access to this function, which is the risk. We only have access. We only can evaluate the empirical risk by computing the average loss over the training error. So what we do then is we take the gradient. We compute the gradient at the current, let's say at the kth iteration, and then minimize this linear approximation. So gradient descent is based on the idea to locally minimize a linear approximation of the function. And since we want the linear approximation, the gradient method only works for differentiable function, which by definition or there exists such a linear approximation at each point. That's basically the definition of differentiability, that you can at each point find a tight linear approximation, which is a tangent to the graph of the function. Any questions up to this point? So what should we then do if we have this local linear approximation? Well, an idea would be to minimize this, to compute the new iterate for the weight vectors by going down, finding the minimum of this linear approximation. But this is not useful as a criterion, because if we would continue this, we would continue till ad infinitum. So this goes down forever. That's why in gradient descent, we minimize only in a neighborhood. So this might be also called a trust region. So we only minimize this local linear approximation in a neighborhood. And this neighborhood is then defined by a parameter, which is called the step size, called this alpha k, which might be different. So this local region over which we minimize the linear approximation might be different for different iterations. So this is called the step size or a learning rate. This is maybe the most important parameter of gradient descent. So we update then the weight vectors. We get the new weight vectors by taking the previous one and minimizing this linear approximation, which is basically go into the opposite direction as the gradient by but scaled by the step size. So we don't minimize this linear approximation exactly. We only minimize it over in a neighborhood, and this neighborhood is defined by this step size parameter. Okay. So that's it. That's the basic idea of gradient descent. And it seems very simple or very basic, but it turns out that small variations of this basic gradient descent are the most widely used optimization algorithms for machine learning methods. So these gradient descent algorithms are often used in a dot-fit function. So whenever you solve this empirical risk minimization problem, for example, finding the best weight vector of a linear hypothesis in order to minimize the training error, you do this with a dot-fit function. What the dot-fit function does, it runs a sufficiently large number of gradient descent iterations or steps. Okay, so any questions at this point? Okay, so there are two parameters here then for gradient descent, or let's say three parameters, hyperparameters. If we want to write down a gradient descent algorithm, basic gradient descent algorithm, then we need to be more precise in the formulation of this whole procedure. So we need to start with an initial guess. So we need to somehow initialize the weight vectors. For example, could be all 0, all entries of the weights equal to 0, or randomly. Then we iterate the gradient descent steps until we reach a certain number of, or let's say we formulate this more general, until stopping criterion satisfied. We repeat the gradient descent step. So we say, we also need to initialize the iteration counter. So we say W, the next iterate, is the previous one minus alpha k, the step size in the kth iteration, times the gradient at the previous iteration. And we, of course, need to increase the iteration counter by 1. Okay, so two main parameters here are the step size. How should we choose the step size? And another parameter is the stopping criterion. When should we stop? So for the step size, we need to consider two aspects at least. So the step size should not be too large, because if the step size would be too large, we could end up with a new weight vector whose empirical risk or function value would be larger than the previous iterate. So if we have WK, so here we have F, the function value, could be a training error of WK or of the hypothesis that is obtained for the parameter WK. And if alpha, so if we use a large step size, then we would end up with a new objective value which is larger than the previous one. And this is not what we want. We want to find the minimum. So alpha K, the step size, should not be too large. So how small can we make alpha K? How small should we make the step size? I mean, the smallest possible choice, yeah, alpha K should always be non-negative. So should always be larger or equal than 0, because we want to go down in the opposite direction of the gradient and not in the direction of the gradient, which would be upwards, or would increase the objective value. So the smallest possible value would be 0. Is alpha K equal to 0 a good choice? No. Yes. Why not? Why would setting alpha K, the step size, to 0 not be a useful choice? Well, we would make 0 progress. So we would always set the next iterate equal to the previous iterate. We would just stay on the same. Yeah, we don't move at all then. Yeah. So it should also not be too small, because if it's too small, we make only small, tiny, microscopic progress. And we only have finite time typically. You only have finite time to fit your machine learning model to get a prediction. Think about a machine learning model in a self-driving car, which has to deliver predictions in real time or sufficiently fast. So we don't have so much time for too many iterations. So alpha K should also be should not be too small. Okay. So what would then be a good choice? Well, one possible way would be to make this alpha K decreasing over iterations. So for example, set alpha K equal 1 over K. And it turns out that such a choice, if the objective function is convex and so differentiable and convex, you will always manage to so if you repeat the gradient steps sufficiently often or for sufficiently large number of iterations, you will always converge to the optimum of the function. And more generally, the necessary and sufficient conditions for the step size are infinite summability. So if you sum the step sizes itself, they must diverge. So this must grow without bound, this sum. If you start counting at 1 and you sum more and more of these step sizes, should be go to infinity. So this means, or this corresponds to the requirement that alpha K should not be too small. This is the mathematical formulation of this intuitive or informal requirement, should not be too small. But on the other hand, it should also be it should not be too large. And for this, we require alpha K squared is finite. So if you sum the squares, this must converge or should converge to a finite number. Yeah. Here's a comment. Yes, so there are more advanced versions for choosing the step size. So one could also think about observing or monitoring how the function values. So in each iteration, you get a new function value. So you get function value W1 in the first iteration, then you do a gradient step, you get the new function value, and you could look at how fast do these function values decrease, or do they decrease at all? And based on these observations, you tune or you adapt the step size. So one way to do this in a more principled way is you look at the current iterate. So this would be W1. And you make a guess, or you make a prediction. Again, here's a prediction. You make a prediction for how much the function value should decrease for a certain step size. So let's say you choose a certain step size and you evaluate the decrease of the linear approximation within this step size, or the region that is determined within the step size. And then you get a new, so you do the gradient step, you get a new weight parameter, and you can then evaluate the function value at this new weight parameter. And you can then evaluate the discrepancy between the predicted decrease. So this was now poorly drawn. Let's make this more precise. So you make your linear approximation that is used in gradient descent, and you choose a certain step size that defines how far you want, or in which neighborhood, in what size of neighborhood you want to minimize this linear approximation. So you have here the previous iterate, then you do the gradient step. You get then the next weight vector, and then you can evaluate this discrepancy here between the decrease that is predicted by the linear approximation and the actual decrease that you can then evaluate when you know the new iterate. And if this discrepancy is too large, then you know that you were too optimistic. So the linear approximation does not hold well within this neighborhood. You should look at the smaller neighborhood. You should make this step size smaller. So for example, divided by 2. And this is a more elaborate or more fancy way to adjust the step size as you continue iterating the gradient steps. Yes, so there are more advanced ways, but actually it turns out that quite often people use such fixed iteration varying step sizes. This is also sometimes called, so this function or this sequence of step sizes as a function of the iteration is also called a learning rate schedule. Learning rate schedule. Okay. Any other questions regarding step size selection? So there's also another way to choose a step size, which is make stronger assumptions on the objective function. So the more we know about the objective function, the more we might be able to guide the choice of step size. So in particular, if the objective function is the training error in linear regression, which means it's 1 over m sum from 1 till m. The ith label of the ith data point minus the predicted label of the ith data point. So yeah, here, for example, we can also say that we can find a closed form expression for the gradient. So the gradient would be here 1 over m times or minus 2 over m sum I equal 1 till m xi times yi. So we get a nice formula for the gradient. And we can also say more about possible choices for the step size, because we have then here in this case that the objective function can be written as a quadratic form, or let's say the gradient itself. The gradient itself can be written as a matrix vector multiplication. So we have W times X. Let me. X transposed times W, and then we need to collect the label vector, which is X times Y. Yeah, should be like this. Minus, here I forgot a minus, so it should be here. Minus 2 over M. And here we have X times Y. Okay, and this feature matrix X here is obtained by stacking the feature vectors of the individual data points into the columns of a matrix. Yeah, so this is called a feature matrix. And then we have the label vector. Y, which is obtained by stacking the labels of each data point into a vector. So this is Rm, this is an Rm, and this is a matrix of shape D times M. Yeah. Okay. And it turns out for this type of objective function and for this gradient, the gradient step becomes a matrix vector multiplication. So let me insert now the gradient into this formula for the gradient into the gradient step. So we have WK plus 1 equals WK minus alpha K. And here we evaluate the gradient 2 over M X times Y minus X transposed WK. Equals further, so we collect terms now. WK, let's put this here. Identity plus minus alpha K 2 over M X transposed WK, and then we have here plus alpha K 2 over M X times Y. Yes. So, and this here is a matrix, by the way. So this is a single matrix. Let's call it, let's be more precise. Let's collect this here. This is a matrix Q. Let's call this matrix Q. And then we have here, this matrix is 1 minus alpha k times Q. So let's collect all this here into a matrix Q. And it turns out that these iterations, they converge if and only if the spectral radius of this matrix here, which is the magnitude of the largest eigenvalue, is smaller than 1. So here the spectral radius of this matrix, which you could think of as an amplification factor or amplification factor of this matrix, this must be smaller than 1. If this is satisfied, these iterations will converge. Yeah, and they will converge to the optimum. So they will converge to the minimum of this empirical risk. Okay, and yeah, I have worked this out in more detail in the lecture notes. So the sufficient condition is that alpha k is smaller or equal than smaller or equal than 1 over the, where do we have it? It's the largest eigenvalue. So let's call the largest eigenvalue lambda 1 of k. Okay, so how can we control this eigenvalue of Q? So the Q matrix here, let's write it down again. The Q matrix is 2 over m times x transposed, where x is the feature matrix. So in this matrix, we collect the feature vectors of the data points. How can we control the eigenvalues of this matrix? Yes. So by making these vectors small in magnitude, and one way to make them small is to standardize them. So to take the raw feature vectors x and divide them by the norm of x, for example. That's how we can make, if this would be too large, that's how we reduce the largest eigenvalue. And the point is, if we use a fixed learning rate or fixed step size in gradient descent, let's say 1 or 0.1 or 0.01, whenever you use a fixed value, you must make sure that this condition is satisfied. And one way to make sure that this is satisfied is to make these eigenvalues of the Q matrix sufficiently small. And the eigenvalues, they depend on the size or the norms of the feature vectors. That's why you often standardize or normalize feature vectors. So one reason is that then you can use absolute values or absolute value for, or a default value, let's call it a default value for the learning rate in gradient descent. And you still obtain or can ensure convergence of gradient descent. Okay. Any other comments? Yeah, it turns out that if you not only have a sufficiently small largest eigenvalue, so lambda 1 Q is the largest eigenvalue, let's call this the largest eigenvalue of this matrix, and lambda D would be the smallest, eigenvalue. Then if you have a lower bound, so you know that lambda dq is larger or equal than some constant, which is smaller or larger than 0. then you can show that this gradient descent steps, they converge at a quite fast rate. In particular, the distance of the kth iteration to the optimum, or the squared norm, this converges exponentially fast, or we call it at a linear rate. So there's some factor, and this factor is, if I'm right, kappa minus 1 divided by kappa plus 1 to the power of k times the distance of the initial choice for the parameter vector to the optimum. So in this kappa here, this is called condition number. This is the ratio of the largest eigenvalue to the smallest eigenvalue. Yes. So here we also see that these eigenvalues, or in particular the ratio of largest to smallest eigenvalue, they have a direct impact on the convergence speed. So how fast a gradient descent step, how much progress a gradient descent step makes towards the optimum. So here would be the optimum. And the smaller this condition number, which is always larger or equal than 1, by definition, the smaller this condition number, the better. In the extreme case, if the condition number is 1, if we insert 1 here, we get here 0. So this would mean after one step, you're at the optimum already. And this is rare. So in practice, we have condition numbers larger than 1, and typically, or unfortunately, often much, much larger than 1. Excellent comment. Yeah, one comment here. Question, if the features are uncorrelated, doesn't that help? Yes. So one way to shape this matrix Q in order to make this condition number closer to 1 would be to transform the features such that they are realizations of independent random variables. So we call this whitening in signal processing in particular. So if you manage to take your raw feature vector, the ith feature vector, and compute the new feature vector x tilde, such that this feature vector is well approximated as a random vector with zero mean and unit covariance matrix, then you can show that this quantity here becomes closer to 1, or approaches 1 for larger and larger data sets. Yes, so making the features, or using uncorrelated features in the sense that they can be approximated by or can be interpreted as realizations of independent random variables, will typically result in this matrix Q here being well conditioned, meaning that the condition number, the ratio of largest to smallest eigenvalue, is close to 1. Yeah, by the way, another way to tune this speed of or the convergence speed of gradient descent is to change the objective function. So it turns out if you don't use, or if the objective function that you minimize is squared error loss, or the average squared error loss over the training set, plus an additional term, let's call it plus lambda squared Euclidean norm. By the way, do you know which machine learning method uses this objective function? Which machine learning method learns the parameters of a linear hypothesis by minimizing this objective function? Ridge regression. Excellent. So this is used by ridge regression. And it turns out ridge regression, when you use gradient descent for ridge regression, you again have this linear system for the gradient step. So the gradient step is a linear system, meaning you apply a matrix to the previous iterate and add some constant vector. in each iteration. So again, for gradient descent in ridge regression, we have this structure, but the matrix Q, whose condition number determines the convergence speed, looks now a bit different. So Q was before 2 over m x transposed, and in ridge regression we get a new matrix that adds an identity term, and this comes from this stems from this component. So if you work this out, gradient descent, you get again a linear update, but the matrix Q, the element matrix Q in this update is this term here. So this would be Q from linear regression that we had before, and we have an additional term, lambda identity. And it turns out that linear algebra tells us that the eigenvalues of this matrix are the eigenvalues of this term, which would be lambda 1 of Q plus lambda. This is the ridge parameter here. And the smallest would be the smallest of this matrix Q from linear regression, also plus lambda. And if you make lambda large, then the ratio between those two goes towards 1. And this is the condition number that determines the convergence of gradient descent for ridge regression. So if you make this regularization parameter larger and larger in ridge regression, this is actually favorable for the computational properties of the method, in the sense that a gradient descent will converge faster and faster. Okay. So this again points at these trade-offs between computational and statistical aspects. So computationally, we would like to use the loss function in ridge regression using a very large lambda. So why shouldn't we then use the largest possible lambda there is always? So from this argument here, the larger the lambda, the better. So why should we then not use lambda 10 to the power of 100 in practice? So computationally, this would be the best. But there's also another aspect. How about statistically? Yes, so statistically, we will converge fast, but we will converge fast to a trivial solution, which is always 0, all vectors 0, and all vectors 0 might incur a very large risk on a test set. So statistically, this is not useful. However, computationally, the more lambda, the more regularization, the better. Okay. Yeah, there was also mentioned a question, what's the convergence limit for lasso regression? I'm not sure exactly what is meant here, but also there in lasso, where you would use the 1 norm, there's also a trade-off between convergence speed and statistical properties. But just to point out, you cannot use gradient descent, basic gradient descent for lasso. Why not? Does anybody know why we cannot use gradient descent to minimize this objective function here, which is the objective function of lasso? Excellent, because this 1 norm is not differentiable. This 1 norm, if you look at 1 weight, has this corner here, and at this corner, we cannot find a perfectly fitting tangent hyperplane. However, we can use something called subgradients instead of gradients, which are generalization of gradients. But today I will only talk about gradient descent. Okay, very good. So interestingly, for from a computational perspective, making lambda large in ridge regression is beneficial because it improves the condition number of the underlying linear system that is implemented by gradient descent. Okay. So we talked now about choosing the step size. So one way to choose the step size is just decrease it by 1 over k, for example, using such a learning rate schedule, and it will converge. But it might be converging very slow. So this is the drawback. So this is nice. This choice is nice because it's universal. You don't need any bounds on eigenvalues. You just need to assume that your objective function is differentiable and convex, but you don't need to know any eigenvalues. However, if you somehow know the eigenvalues of this matrix, which you might be able to control to some extent, for example, using feature normalization. If you know something about these eigenvalues, then you should use this knowledge. And one way to use this knowledge is choose alpha, the step size, via these eigenvalues. In particular, choosing alpha smaller than the reciprocal of the largest eigenvalue of this matrix, of this feature matrix. Okay, so that's about choosing the step size, but then there was another parameter or hyperparameter of gradient descent, which is also not trivial, which is the stopping criterion. When should we stop? Any ideas? What would be good stopping criteria? Yes, so we could monitor the function values, which are the training errors for each choice of model parameters. And if this is not decreasing, let's say from here to here we have a decrease by 10 to the minus 10, then we stop. Yeah, another option would be, a very elegant option is to look at the gradient, because for smooth convex functions, the gradient gives us a hint how far away are we from the optimum. So if the gradient is small, or the norm of the gradient is small, then we cannot be too far away from the optimum. Yes, yet another option is to remember that the ultimate goal of machine learning is not to find this optimum of the training error, so to find the weight vector that minimizes the training error, but actually the goal is to find the optimum weight vector that minimizes the risk. And one way to estimate the risk outside the training error is to use a validation error. So we could look for each iteration, we could evaluate the validation error. So we evaluate the validation error for for the hypothesis obtained from the first iteration, then we evaluate the validation error for the hypothesis obtained after the second gradient step, and so on and so forth. And if this validation error does not decrease much anymore, then we stop. And this is referred to as early stopping, because this might happen at the point where, just by looking at the empirical risk, at the training error, we would not be close at all. We would still make progress and making the training error smaller and smaller. However, the validation error would not be reduced anymore. And this is actually useful, because if the validation error does not go down, but the training error goes down more and more, then this is actually a sign that we go straight into overfitting. Okay, so now we have talked about stopping criteria. We have talked about choices of the step size. So let's now move on to some variants of gradient descent. So this is the basic blueprint for many gradient methods that all vary in different ways, how they, for example, compute or approximate the gradient. But there might also be cases where we want the parameter vector to belong to a subset of all possible parameter vectors. So let's say this subset of RD. So one way could be we want to learn a linear hypothesis. We want to learn a linear hypothesis whose weight vector has a norm squared smaller or equal than 10. So for some reason, we want to have such a constraint. This would be an example of model pruning, by the way. And then the question is, so how would we minimize the training error if we have such constraints? So we want these weights to belong to a subset, or this we call a constraint set. And then it turns out that often we can use a small modification of gradient descent, which is as follows. So we start again to improve the current weights WK by a gradient step. doing a gradient step. But the thing is, doing this gradient step might lead us outside the constraint set. So this, the result of this gradient step might not belong to the constraint set anymore. So what can we do? Well, we say this is only a tentative new weight vector, but the really new weight vector is obtained by projection of the tentative update onto projecting this weight vector onto the set C. So and the projection is defined. What do I mean by projection? So this here is a convex set. Yeah, I tested silently assumed that this constraint set is a convex set. Convex. And the projection of another weight vector, for example, this could be the tentative updated weight vector, which is outside the constraint set. The projection is the specific point, well-defined point in this constraint set C that has the smallest squared Euclidean norm to the vector that we want to project. So this point here would be the projection, WK plus 1. And it turns out that this projection is always well-defined as soon as this set C is convex and closed. Okay, and yeah, so this here is then called projected gradient descent. So projected, oh, that's bad handwriting, I'm sorry. Projected gradient descent. This is the extension of basic gradient descent to cope with constraints of the parameter vector. We will see then one application of this projected gradient descent is in an algorithm called federated averaging, where we want to learn weight vectors for different local data sets that are all equal. So we want to train a single model, so with one set of parameters, but in a distributed fashion. And one way could be to locally update these model parameters and then require them to be identical. And this requiring them to be identical is a form of can be represented by a constraint set. So we will see that federated averaging is an approximate form of projected gradient descent. Oh, no, it's actually an instance of projected gradient descent. So it's precisely one example of projected gradient descent. Okay. Another variation, yeah, just to point out without going into too much detail, which you can find in the lecture notes. One interesting thing is that for well-behaved functions, so if this objective function is smooth, differentiable, and strongly convex, which is defined in the lecture notes, just to say that such functions happen to arise in machine learning for several methods, like for ridge regression in particular. Then if the function has these properties, the number of iterations or the convergence speed with how fast this projected gradient descent converges towards the optimum is actually identical to the convergence speed of gradient descent itself. And this is remarkable. This fact that we always project back onto the set C does not slow down the progress as we iterate in projected gradient descent. So in terms of number of iterations, projected gradient descent might be as fast as gradient descent. However, in each iteration of projected gradient descent, we need to compute this projection, and this might be computationally expensive. So finding this point, this closest point to a given point in a convex set might require to solve itself an optimization problem. Okay. Yes, so another variant would be perturbed gradient descent. So in perturbed gradient descent, we cannot, or we do not compute the gradient update exactly. So the exact gradient update step would be WK, the previous one, minus alpha K times gradient but there's an error. There's some error term that is always added to this update or this new model weights. Does anyone of you know why this is useful in practice? Why might there be, what might be the reason to have such error terms in gradient descent? For example, for linear regression, we could compute this gradient exactly. So the gradient would be something like x y minus x wk. And here we have the feature matrix and the label vector. So we can compute the gradient, and we can subtract it from the previous iterate. So why should we take into account an error term here? What do you think? What might be a source for such errors? Well, outliers, these outliers, they would only hurt us if we expect them to be not there. So we would use some probabilistic model. Yeah, here also mini batch. Yeah, mini batch, this also relates to using probabilistic models, assuming that these data points here are IID realizations of some random variable, but without any probabilistic assumptions. Why might we still get some error here when you implement this when you implement this gradient step in, for example, in Python? How many bits can you use to represent these numbers? So this would be real numbers, real valued vectors. Yeah, so there might be numerical errors. You might have quantization errors. You only have a finite number of bits to represent these matrices and vectors. So there might be rounding errors arising, and this you can model by such an error term. Okay. Yes, and it turns out that these errors, they accumulate. Of course, they accumulate over the iterations. So you sum up all the errors over the iterations. And if you, in the worst case, you add up the norms using the triangle inequality, you get an upper bound on the error. So the larger the errors, the worse the resulting accuracy, or the farther away is this kth iterate from the optimum. So you need to somehow make sure that these errors, they become small eventually. So you typically need a requirement that the norm of these errors goes to 0. If you have not such a decreasing errors, then you will not be able to achieve or to approach the optimum or the minimum of the function that you want to minimize using gradient descent. Okay, so, and this brings me to the next variant already, which is stochastic gradient descent. So in stochastic, yeah, and this is also comes nicely into play for the question now here. So there was one question: how do we choose the value of E? So often you do not have control over E. So E might be some error, some failure of the system. So, but what you might know is, you know how fast these errors converge towards 0, or you know an upper bound. You might know, for example, that EK, the norm is smaller than 1. And then you can say something about, then you can make a sensitivity or robustness analysis, let's say. But one example where you have a bit of control of the error is stochastic gradient descent. So the idea in stochastic gradient descent is, instead of the exact gradient, that you need in gradient descent, of course. You use an approximation. You use some approximation GK. So this is an estimate of the gradient, or an approximation. How can you how can you get such an approximation? Well, if you look at the gradient for linear regression, the gradient has this form. So it's 2 over m, I think minus here, xi so it's a sum. And typically this is a large sum. So in big data applications, this might be 10 to the power of 6. So that's why it might also already computing the gradient might be infeasible computationally, because either you don't have enough computation time, or you don't have enough time to sum up 1 million of these components in the sum, or these components, these data points, feature vectors and labels, they are stored distributed all over the planet in the cloud, for example. So one way to approximate this is to randomly pick an index. Let's call this IK. And use as an approximation, we use the component that corresponds to this index. So this would be X, the feature vector at the IKth data point, times Y, IK minus WK transposed X, IK. Okay. And if you choose this index IK uniformly at random, out of the set of all data points, so we have M, then it turns out that this estimate, or this gradient estimate, is unbiased to the expectation of this random variable. Since this here, if we choose the index randomly, then this term here will become random, and we can compute an expectation, and this will be exactly the gradient. Okay, so in stochastic gradient descent, we use again a gradient step, but instead of the gradient, we use the estimate for the gradient. And we can interpret this as a form of perturbed gradient descent. We can say this is the same as a gradient step. But we need then to take into account this error term here, which is the difference between the gradient and the approximation. So this stochastic gradient descent is an instance of perturbed gradient descent, where the perturbation, and this now is the important property here, the perturbation is scaled by alpha k, which is the step size or the learning rate, which we can control. So by making the step size small, we can make this error smaller in stochastic gradient descent. So the best case would then be make alpha k 0, because then this error term would also be 0, would vanish. Why should we not choose alpha k equal to 0 in stochastic gradient descent? Yeah, again, it will not do anything. It will not do anything, but at least we make 0 errors. We introduce 0 errors, but we also make no progress. So no risk, no fun, so to say. But yeah, we should also make not alpha k too large, because if we make alpha k too large, then also the error will be large. So again, there's a trade-off. And what is your guess? How could we choose alpha k? What would be a useful choice for the step size? Yes, 1/k. And the interesting thing here, this is the last thing I will just mention without going into much detail. When you use stochastic gradient descent to train a linear model, so let's say you have your we have our training set, which consists of m data points, m data points. So then we could think of actually that this term here is a realization of a random variable with distribution p, x, and y. So this would also mean that the squared error for this term here that we get for this term, so the squared error for this first term would be w transposed x1 minus y1 squared. So this would be a component of a squared error. And we can also compute the gradient of this first component. So the gradient of this first component would be x1 times w transposed x1 minus y1. And since this x1 and y1 is an IID realization of a random variable with joint distribution x and y, this means that actually this is an unbiased estimator for a gradient of the risk itself. The risk itself, which is actually what we want to optimize. So we are not fooling around anymore with minimizing the empirical risk, which is just an approximation, but now we look at the gradient of the risk itself. So this seems, I mean, this would be ideal. The ideal case would be to do gradient descent, for the risk itself. So to go down the gradient, the opposite gradient, by using the gradient of the risk. But the problem always was that we do not know the risk. We only know IID realization. But now we have the tool to solve this problem, because we can say, instead of using the gradient, we use a noisy estimate of the gradient. So we use this gradient of the kth data point. So we sequentially go over the first, over the second, over the third, until the mth data point, and use each new data point to do a new stochastic gradient descent iteration. So where do we have it? xk wk transposed xk minus yk. So this is the kth data point. In each iteration, we read in a new data point, and we use this new data point to compute an estimate for the gradient of the risk itself. We are not talking about the gradient of the empirical risk anymore. We talk about the gradient of the risk itself. So, and it turns out, but I will just refer then to the relevant papers in the lecture notes, that this achieves a risk. So if you then use if you look at the expected loss of the hypothesis after m iterations of this stochastic gradient descent variant, then this decreases, so it's proportional to 1/m. So this decreases with 1 over the number of data points that you have read in. And if you compare this with the results I have shown in, or with the analysis of the validation error and the generalization error of plain linear regression in section 3, you find that 1/m is optimal. So with m data points, you can never learn a hypothesis that has a risk smaller than 1/m times some factors, which we ignore here for simplicity. But this dependence on the number of data points is optimal. of basic stochastic gradient descent. You don't need any acceleration tricks, anything like this. Basic stochastic gradient descent achieves the optimum dependency on the number of data points that you have in your training set in terms of the risk that you obtain from the hypothesis for this weight vectors. And this is quite remarkable. So this basic stochastic gradient descent is in a certain settings optimal. So there's one question, isn't stochastic gradient descent much slower because we can't calculate the gradient in parallel? Yeah, so this refers to the fact that we can reduce this noise term here. So this gradient noise, the difference between the estimate of the gradient and the true gradient at the kth iteration. So this noise, we can reduce this noise by using for this gradient estimate, not using a single data point, but using a mini batch. So we call this mini batch. And this might consist of, let's say, B data points, which are indexed by I1 till IB. And then we compute the gradient estimate. The gradient estimate over this mini batch, 1 over B, X over all data points in the mini batch, Xi times WK transposed Xi minus Yi. Yeah. And yeah, if this noise is smaller, so the errors is smaller, you will typically get better results after, or get more close to the optimum after the same number of iterations. So I'm not sure if this is related to that question, but we don't take into account any parallel computers here. Okay, yeah, we are almost at the end of this lecture. So are there any other questions regarding gradient descent?